Hi, everybody. Last micro talk for this workshop, so I'm gonna try to finish up before we all fall asleep. All right, yeah, my name is Alex Bulekov. I'm a PhD student here at Boston University. My advisor is Professor Manuel Egle, and I'm an intern at Red Hat, and I'm excited to present some of the work we're doing on hypervisor security. When the cloud came around, it enabled all these companies to move a lot of their computing that was going on their individual clusters into the cloud. One of the killer features for the cloud providers was that they could run computing workloads for these companies on the same hardware. And this really allowed cloud providers to drive down costs and enabled unprecedented scaling. And what allowed for this to happen is really the underlying technology, which are hypervisors and the virtual machines that they run. And the other thing that really allowed for the cloud to take off was the fact that these companies, they didn't really need to do too much to their computing workloads to move them to the cloud, because you could move whatever operating system you were already using and whatever applications you were already using, and usually with quite very few changes, you'd be up and running on the cloud. But as you can imagine, it's no simple task for the hypervisor to really provide this virtualization layer which allows you to run an existing operating system and an existing application. And there's some pretty tricky situations you can get into. So if you have, for example, a compromised virtual machine, whether the tenant it was malicious from the start, or maybe one of their applications got hacked and the virtual machine was taken over. What the worst case scenario for the cloud provider is for this infection to get outside of that individual virtual machine, compromise the underlying hypervisor, and maybe even access the other customers' data or virtual machines that are running on the same physical node. And so the security, before companies had a way to protect this one, they had their own data centers. They could just hire a security guard and put them in front of their data center. But now they had to, now the thing that's protecting these companies from each other, who are often running running their workloads inside the same data center or even inside the same nodes, is this interface, which is the virtualization interface or the virtual devices. And this is such a critical interface that we'd expect, the code to be perfect and there to be no bugs in there. But unfortunately, this isn't true, and there's bugs that are found every month, sometimes every week even. And every time one of these bugs shows up, it's a big wake-up call that we have all this software that we're putting a lot of trust into, and not just the cloud providers are trusting this, but also all of the people that are using shared infrastructure. And if we look at what the job of a hypervisor is, well, mainly one thing it has to do is it has to split up the computing resources, so the CPU, between all the virtual machines. And fortunately, a lot of the complexity of doing that was moved into the hardware around 15 years ago, when all the major CPU vendors added support for virtualization. But we also have all of these other devices that virtual machines and operating systems typically rely on. And unfortunately, a lot of these devices are still implemented in hundreds of thousands of lines of C or C++ code. And as we know, this code often has bugs. And if we look at how operating systems and typically interact with these devices, there's three major interfaces. So on x86 machines, there's a 64K space of addressable I/O ports, which are dedicated to interfacing with devices. We also have memory mapped I/O, which are ranges inside main memory, which are mapped instead of to the DRAM, they're mapped to I/O operations. So maybe you'd have a range that's mapped to all the pixels on your video card. And then we also have direct memory access capable devices, where basically the OS can write the address of some data located at some random location in memory via port I/O or MMIO to a device, then the device will asynchronously, without the CPU's involvement, go ahead and fetch that data and do whatever operations it needs to do. And that allows really high throughput devices such as VirtIO or such as network devices to do their job without the CPU being constantly involved for every byte that needs to be sent on the network. And so our work, we implemented our work for the open source Chemo hypervisor. And if we look at how one of these bugs might be manifested inside Chemo, so if an attacker crafts a sequence of malicious port I/O and memory mapped I/O inputs, they could potentially break out of Chemo's virtual machine confinement and into the host. And our goal is to be able to find these malicious inputs before the attackers do. And the way we do that is using fuzzing. And from a mile-high view, I guess fuzzing is just a way to provide randomized inputs to virtual devices in hopes of triggering bugs so we can reproduce them and patch them. But as I mentioned previously, the input space for virtual devices is enormous. So even if we think about just RAM for a 64-bit machine, we're talking about exabytes of valid addresses. So how do we actually how do we reshape this input space in a way that the fuzzer can actually interact with all these devices in a meaningful way? Well, the first thing that we can do is we can actually leverage APIs that the hypervisor already provides to enumerate all of the regions that are directly mapped to I/O devices, such as through port I/O and through MMIO. And that takes care of that part of the equation. But then we also have the direct memory access part, which is data that can live anywhere in memory. And the way we deal with that is that we hook all virtual device accesses to DMA ranges, and when we see a device trying to access some data inside main memory, we populate that data just in time, so we don't have to worry about about figuring out a priori where is the DMA data gonna live. And so overall, I mean that was a very quick overview of like some of the techniques we use for our system, but we also need to worry about enabling all of the I/O mappings and then enumerating the space, and then finally in our fuzzing loop, we not only do we need to generate the various I/O patterns and interpret them into actual I/O actions and handle DMA just in time, we also need to reset the state of the virtual machine after each run to make sure that there's no state leaking in between different fuzzing runs. And so as I mentioned, we implemented this for Chemo, and thanks to the resources that are available at the MGH-PCC, we were able to fuzz hundreds of different Chemo configurations in parallel. And one thing that we look at, for example, is how the coverage, so how the amount of code that we run in Chemo increases over time. And we can even zoom in on individual source files and look at individual virtual devices and see what percentage of those virtual devices our fuzzer has covered, and we can zoom in even further and look at the individual lines and use this to basically make iterations on our fuzzing technique and see how we can further improve the coverage that our fuzzer achieves. And we've already found bugs in devices such as the VirtIO class of devices, the Chemo's serial device, the MegaRAID card, and there's a lot more on the way that we're still in the process of triaging and communicating to the developers. Our work is already upstreamed into Chemo, so other developers are free to use it and use our framework to implement their own types of fuzzers. And due to Chemo's popularity, it's not only used in software that we know and love, such as Overt and OpenStack, but there's stuff like Nutanix, Proxmox, and like all of these other systems that rely on Chemo. And because of our changes to Chemo, these systems are already safer. And in the future, we'd love to have something that that already exists for the kernel, where for every crash that we find, we build an automatic reproducer program, and then as new code is added to Chemo, we can test against these reproducers to make sure that bugs, that they not only went away after the patch occurred, but they also didn't come back. And finally, we're also actively working on getting our code integrated into a continuous fuzzing service, which would allow for bugs to be caught inside Chemo before they ever even made it into an official release to make hypervisors safer than ever. And I'd like to give a big thank you to everybody who works with me at Red Hat. And if this work sounds interesting to you, here are my contact details, and I'd love to talk to you. Thanks.